Yes, good morning to all. So we'll start in another 3 minutes. Okay, regarding the references, yeah, I spoke to the Will team as well. Even they suggested not to purchase any textbooks. There are some textbooks references available uh, online. Those you can refer to if you get the ebooks. Otherwise, whatever I cover in my slides, that should be sufficient for the your mid-sem and complete.
Um,
Yes, sorry. Yeah. So okay. Um, I think yeah, my mic was off. Okay, so let us start. So in this class, we will be discussing the inter-process communication which happens in distributed systems. So as we discussed in the last class, we have nodes. All these different nodes communicate with each other for doing the distributed computing. And then once the task assigned to a node is complete, the result is sent back to the node that has assigned this task to this node. So we learn more about interprocess communication, how things work, what is used. So to start, we just use a yeah. So when it comes to processes running on different machines in a distributed system, we don't just rely on one computer to do all tasks, and we have multiple machines, right, which are known as node. And these nodes could be geographically distributed or connected using local network. Now, on each of these machines, we have a process, and this process is running. And these different processes, they may have share the memory, or they may be executing in isolation. So now, how do we communicate? So to communicate between these different processes, it is done via network when it comes to distributed machines, and this requires explicit mechanisms. So you need different coordination techniques, and these could be sockets, RPC, or message queues. So we will learn more about how sockets are used, how RPC is used, and how the message queues are used. So to start with the now understanding what is IPC. So interprocess communication, or IPC, is the technique used by processors to exchange data and synchronize their actions. So when IPC on a single machine may be there, we can use shared memory or pipes. We'll learn what pipes are. When it comes to distributed system, in distributed system, you have to uh, you have to talk with other processes using messages. That is message queue. Now, IPC is very important because it's the foundation of services such as cloud storage. If you have online games, or even the Netflix backend that we watch, Netflix uses IPC, where the data is sent from the master node to different slave nodes. So now in distributed systems, the fundamental characteristics is that these processes run on different physical machines. And we've discussed this in detail in the last class as well. Sometimes these different machines could be in the same data center, or spread, spread across different places across the globe. But these processes cannot work in isolation. They have to communicate. And why do you think they have to communicate? Anyone? Points are here. Anyone wants to elaborate?
Ma'am, because distributed computing is all about a single program into multiple tasks.
Yes.
So they need to club at the end.
Yes, we need the results at the end, or we have to at least ensure that whatever task is assigned to that system is complete. Okay. The first reason could be that we want to share resources. So let's say one machine holds a data set and another might have a compute power, and we might need another machine which will manage the access control of these machines. So these processes of different machine will coordinate to share these resources. We may also have a client server model. Now, in client server model, what happens is client will request some service, and the server has to respond over a network. Any examples anyone can think of? an example of a client server paradigm?
Uh, yes, ma'am. One example is like when we are working on Kubernetes services, like there are two nodes. I mean, there are
Hmm.
multiple nodes, but two major group of node is a master and slab node, we can say, or master or user node. So both nodes are different, but they have to communicate each other. And master node is managing all the API call, whatever API call coming from outside. First, it is hitting to a master node and master node is sending that call to different worker node and the worker node are distributed.
Okay, yeah. Your yes, your yeah, your example makes sense and is correct. But master slave and client server are two different types of paradigms, which we will discuss in the later slides as well. But yes, your example holds. You can think about a DNS server, web server, even database servers, which are mostly distributed, fall in under this category of client server.
Ma'am, DNS is there,
Uh,
DHCP is there, certificate authority,
yes,
all
yes,
these things are there.
yeah. Agree. So, other than that, yes, cloud-based systems like Netflix or even Google Docs, these are all, you know, composed of microservices which are working in parallel across different nodes, and they all are tightly, you know, put together or coupled through communication. Other than that, we can think of reusable software components such as authentication, logging, or even recommendation engines. These are all independent modules that can be used or reused across systems, and they have to communicate. And then, you know, uh, through this communication, we have the complete application that we see on our systems. Other than that, we do have some good engineering reasons. Anyone can think of what could be the good software engineering reasons why we need these processes have to communicate? Any guesses?
Security could be one of the reasons.
I think
Uh,
for dealing with
hmm,
computation overhead, I think you mentioned last time also, so that um, the I mean the resources are distributed across different nodes and we get faster outputs at the end.
yes, yes. One, yeah, I agree. So basically, first of all, it allows us to scale better, right? We can have large having multiple systems helps us to scale and be able to provide services to more and more, clients, or more and more users, right? If there is only one system, then it obviously after some time it will get locked due to insufficient bandwidth for able to handle those many requests. So we are able to scale better, handle, even if there is some failure, we can handle it gracefully because there are multiple, the work is distributed among systems. So even if one system fails, some other system can take care of this responsibility. And
I can give
uh, yeah,
I
yes.
can give I can give a enterprise example here, whatever we are using, and everybody
Hmm.
enterprise is using those kind of things. Like
Okay.
we have microservice architecture, and in
Hmm.
microservice architecture, like example, different modules. Some modules are solving a AI related chatbot is running on
Hmm.
that microservice that node, and in some node we have authentication. We are separating all each modules on different node so that dependency will be very less. Like if let example
Hmm.
authentication is not working, it not mean your chatbot will stop or something will stop. In that case, multiple nodes needs to communicate each other to fulfill entire software paradigm.
Yes, yes, I agree. So you
Ma'am,
have to distribute your work among multiple nodes. Yes.
correct. One of the important software engineering principle is separation of concerns. So based on the work which needs to be done, there could be separate responsibilities figured out, and specific dedicated hardwares could support that
Mm-hmm.
particular task in a much more efficient way. That way we can separate them, and we can, based on the task which needs to be handled, that machine will be
Yeah.
more able, as in for database related activity we need something which is more in context of database size and so
Yes.
forth. If we consider
Yes.
computation as a separate activity, then for computation there are different needs. A machine
Yeah.
which
You
takes
need.
up, sorry, gone.
Agreed. Yeah. 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 You need more
Machine,
uh, performance-oriented machine,
correct.
whereas
Mach- right.
for database you need a storage-oriented machine.
Storage oriented machine, right? The machine which takes up the request from clients has a different
Mm.
set of requirements. AI related node will have different set of requirements. So those responsibilities could dictate what kind of hardware support is required, and that way
Yes.
we can separate the concerns. As you rightly said, we can scale them up based on the need, as in database server
Mm-hmm.
could be scaled up based on its data needs over the period of time. So that way we can segregate those responsibilities, and that's one of the important software engineering principle which will be taken care.
Agreed. 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 You have put it uh, in a really you know detailed manner. I think so. We are quite clear of how this what are the software engineering needs or reasons for having this distributed systems. So, yeah, moving on. Now we have distributed systems, but this also brings challenges, right? So, anyone wants to talk about these three challenges: latency, message loss, failure?
Yeah, typically, ma'am, wherever we kind of communicate between two systems, it has to, if we consider single machine and if two processes need to talk to each other, they will talk in a faster way because they just have to consider the addresses by which they are going to be far in the same node. But when we talk about distributed system, the systems could be away from each other, maybe in same LAN or WAN, or even besides data centers, other data centers, and those data centers could be across the countries also. So that way we'll need to be careful about latency, as in based on the use case, we'll need to consider how much latency is permissible and so forth. And then
Yes,
importantly, we cannot have kind of instant responses that way. Since
yeah,
machines are going to be talking to each other over network, we'll need to be cognizant about that part. And then the other
yes,
node is not available. Those kind of things are going to be there. Then
yes,
processing
eh,
speed of the machines is also, one machine is taking, let's say, 100 requests per second, while other may not be in a position to respond to 100 requests per second. So those aspects comes into picture. So latency, and then if there is a difference in speed of those machines, message loss could be there, and then failure of the nodes may not kind of complete the journey that way. So we'll need to be cognizant about failure part, and we'll need to have a mechanism so that those also gracefully could be handled.
yes, yes, you're right. So, even on fast networks, message round trips do take time, and with scale, even having milliseconds add up in this latency. Also, packets may get dropped, or they might get reordered, and even if you use protocols like TCP, but still there will be cost involved. And failure to, we all know, machines crash. So networks, they are partitioned, and uh, there are, like, we can expect issues in distributed systems as well. So every time we design a distributed software, we must ask ourselves, how do the process talk? What happens if they are not able to communicate? And if they fail, how can they recover? So these things are very important when we talk about process communication. So there are, from OS perspective, how the IPC is treated is that it is done using two things: shared memory or messages. In shared memory, OS will set up the job, then it might have to take care of synchronization, but transporting of data is not the headache of an operating system. It is taken care of by the memory because memory is shared between the processes and they manage. In message passing, OS is involved in every step. OS is responsible for transporting the data. So, what kind of connections are available when it comes to instruction inter-process communication? So here there are two types of communication. The first is connectionless. Sorry, I said communication. Connectionless. In connectionless, the IPC mechanism does not need any preliminary setup. When there is connection, it requires proper negotiation and setup before we start the data flow. So in connectionless, what happens is typically there is no permanent data structure which is shared in OS by the sender and the receiver of communication. This is great for a quick and short communication, but when we have large and frequent communications, this is not ideal. At the same time, because there is no connection which is already set up, each communication takes more OS resources per byte. With connection oriented IPC, sender and receiver will arrange the delivery details. OS will typically save all the IPC related info for them, and pros and cons are almost the opposite of connectionless IPC. So these are the 5 basic IPC mechanisms, which we'll see one at a time, and then we'll move to some real world, IPC approaches that we use. The first one is file system. So as you can see in this figure, sender processor will write data to the file. Receiver will read it from it. So how the synchronization works is the file have to be locked or unlocked. The other type is using messages, which we have discussed explicitly and will continue to discuss. Here, the sender will format data into a formal message. This message from processor A will be sent to OS, and then OS will send this message to the process B. The receiver will read the message from the queue, and there is an option in message based IPC where the sender might get blocked or not blocked till the message is received by the processor. It depends on what mechanism is used. The other type of IPC is procedure called IPC. Here, same procedure called interface is used, where what we do is we have a function. This function, when we call, will send a request. This function will send a request to the server, and then the server will send the results. Anyone knows what an example of procedure called IPC?
In cloud, we are using, especially in Lambda, in AWS, we are using Lambda, where we are using this kind of activity. Like if
Okay.
you call a function, then that will send a request to you.
Server.
Yes, sir.
Yeah. So such functions, we will also discuss one of them in the later class. But yes, that could be one example. Anyone?
Multi-threaded, as in multi-threading. If we consider multi-threading as an example, then there could be different processes, and then main method can invoke a method on another thread, which will do. Let's say we need to compute sum of n number of elements in an array. Then there could be multiple threads which could chunk them up, sum them up, and can send back their response to me, and which will aggregate their responses and provide the final sum, something of that sort. So multiple process would be involved, and each process will do the job of uh, considering that bucket of data only.
So this could be an example of MPI, right? Through MPI, we send a call and from one process to another, and then the result will receive from the other process. So if there are special functions, basically, this procedure call is the function should be able to take care of this calls to the server. Okay,
Okay, so
and
does that
just
mean
calling that
process?
function will ensure that the that when user writes this code, user will only write that function. Will not mention all the details of how the communication needs to be done. The function will is designed in such a way that it will take care of the communication.
Okay, does that mean
Yeah.
process A and process B are running on different hosts, different nodes?
Yes. Good.
Okay, okay, yeah, that helps. Thanks.
The shared memory IPC is where we both the processes. In this case, if the memory is shared, that means they are not happening on the different machines. It has to be in the same machine, or or two processors are connected to the same memories. In this case, the communication happens through memory. That is, if say process A modifies this variable x, this value is stored in the memory, shared memory, and when process B reads this memory by when it wants to print, it will use the same memory stored. So here the communication is through the memory. So here we might have to use locks or semaphores to ensure that there is no data race. That is, if one process updates this value, before the other process reads it, we have to log this data. Otherwise, it might so happen that the process B reads some previous value or a modified value, which is an incorrect value. Hence, here synchronization is very critical. So, as I mentioned, synchronization is very critical in IPC. So, how do we send and receive processes and ensure that the synchronization has happened? Now, how anyone has used any kind of synchronization and has worked with any synchronization techniques?
Uh, there is one which I aware about that. Like all the host, there are central host which is sending a single packet to in every 5 seconds to each host to make synchronization. Like all are in a sync or not.
Okay, okay. So
Synchronization
yes,
techniques.
yeah. Hello, hello. We missed what you said.
Ma'am, one kind of synchronization could be an example where there are multiple applications trying to access a common database. So let's say, for example, there is an RDS database and multiple applications are trying to update the data at the same time. So at
Mm-hmm.
that time, it might create a deadlock kind of a situation. So, or basically, we get incorrect outputs because of deadlocks. So,
Mm-hmm.
yeah, so at that time,
So
we need to place a transaction lock on the database kind of a thing. So, therein
yes, yes,
synchronization is involved.
yes. Where locking is a very powerful synchronization technique, where you ensure that the data is used by one process at the same time, or one you know activity at the same time, so that the data is not corrupted. So
Yeah.
locking is a very powerful synchronization technique. So one so here this is one approach where we both sender and receiver are blocked. That means when the sender sends the data, the sender is blocked till the receiver receives it, and then it can continue working. Okay. The other approach is where there is no blocking sender. So sender will issue, then it will proceed without waiting to discover whether the message is received or not. The receiver will wait for message arrival, and once the message has arrived, it will start processing. There is another approach where there is no non-blocking send as well as non-blocking receive. Here, neither party is blocked. Sender will proceed after sending the message. Receiver will work until the message arrives. Once the message arrives, the receiver will continue working and or have some kind of use some kind of interrupt that once it is delivered, it will read the message and then continue working. So both the sender and receiver are not blocked. But depending on what kind of application you are working with, you have to choose which type of synchronization techniques works for you. Now, how is the addressing works in IPC? Anyone? How does the standard specifies like where this data is going? So to processor communicating maybe in a shared memory system or a distributed system, you need addressing, right? You need to specify what is the sender address, what is the receiver address. It is very important to know which two processes are communicating. So there are different types of addressing. First one is direct addressing. Here, sender will specify the name of the receiving process. It can use some kind of unique process names, and receiver also can specify what are the names of expected senders. So, or it is ready to take any data coming from anyone. This is known as direct addressing. In indirect addressing, what is done is data is sent to queues or message queues, mailboxes, or any kind of shared data structure or buffers that are there. The receiver will perform some form of read on this data structure. It will read from this message queues or it can read from this buffers. This is flexible because then the sender and receiver are not completely dependent on each other, but there is a third data structure which takes care of passing this data. So there are different types of inter-process communication mechanisms which are available specifically in Unix, which are like pipes, message queues, semaphores, shared memory, sockets, and RPC. We'll see each one of them and then we'll go in detail for some of them. So, anyone knows what pipe is, or what do you think it is?
Pipe is a
This,
way of,
hmm,
I mean, where it takes the output from one process and share feed it as an input to the another process.
yes, you're quite close. So, this is one of the very early IPC mechanism. Okay, and this may not very work really well when it comes to now the current large scale distributed system. The reason is it is unidirectional mostly. The data is unformatted. Then and the interprocess there are interprocess byte streams where which the data is transferred, and it is almost very similar to a file. So what happens, as you mentioned, one process feeds bytes into the pipe. The second process may read the byte. This and if you are doing it other way, you cannot do it. You cannot have the same pipe which will read and write read from sender and write to client or child process, or you have a reading. So you need a separate pipe for different directions of communication. So what happens is when we are trying to write more bytes than what the pipe supports, this will make the this will block the sender until the receiver has the capacity to read some more data. In case if we are reading bytes when there are no available bytes from the receiver, the sender will wait until the sender writes some bytes. But what is the advantage of pipes is because there is single pipe with bounded capacity, this cannot cause a deadlock as such because it is unidirectional anyway. This is which is very popular is message queues. Like pipes, the data is organized in messages, and these messages are uh, a bit similar to pipes, but they because they allow the data to be passed between processes. But there is a key difference. Unlike pipes, message queues organize data into discrete self-contained messages rather than a continuous byte stream. Each message will have typically three components. The first one, identifier, which will let the process filter select specific type of messages. There will be a length field which specifies how much data is in the message, and then the last part is the actual data which is being transferred. So this structure helps message queues, especially in useful. This is useful in scenarios where we need asynchronous communication. That is, everything need not be in a synchronous fashion or one after the other. So here, what we can do is we can manage or prioritize different types of messages. Also, we can decouple the sender and receiver process. That is, they don't have to be active at the same time. As long as the data is in message queues, this helps them to get the flexibility in terms of when we have multiple processes. They do not sender and receiver need not be active at the same time. As long as data is in message queues, the data will get delivered. So semaphores were introduced in again Unix in release 3, and they are mostly used for synchronization since they only communicate one bit of information, and this is used mostly for shared memory because this works only in the shared memory systems. So in shared memory, what happens is this allows two or more processes to directly access a common memory segment. This provides the fastest form of inter-process communication over distributed because the memory is shared and you can access it anytime. So, but yes, there are there are disadvantages as well. Now, what is the role of process here? Is the OS will ensure that it has the control over access permissions of this memory. It will decide who reads, writes, or does both, which process is allowed to. But when it comes to shared memory, synchronization mechanisms are very critical. Semaphores are used or locks are used to avoid these race conditions. But although synchronization creates the issue, shared memory is especially useful when processes needs to exchange large amount of data very quickly because it is the fastest way we can communicate. It is also used as the foundation for building the user level threads or packages which are used for the custom multi-threading frameworks in Unix. Anyone wants to talk about sockets, how they work? We'll talk more about it in the later slides as well. But anyone wants to talk? What are sockets? How they work?
Socket is, as in, if we consider pipe, it was one way. But if we consider socket, then it kind of works as a pipe which is bidirectional, as in both the parties could send and receive the data in both the
Mm-hmm,
directions. And that's kind of a continuous connection, which is
mm-hmm.
like initially, if we consider HTTP based stuff, then one party sends a request, and then once it receives the response, the connection is broken. But socket is kind of connect
Yes.
kept between those two
Mm.
parties so that either of the party can send and the other party could receive the data, and it could be data can flow in both the directions, more importantly.
Yes, agree. So sockets are like the flexible and very powerful IPC mechanisms. It consists of two endpoints, one created by the source process, the other is for the destination process. And what makes these sockets particularly powerful is that, as you said, versatility. They can be used for local communication between processes using on the same machine, as well as for networked communication between processes on different machines using the uh, internet domains like we use TCP, IP, UDP, and hence the sockets are like the they provide the low level building blocks for the most network communications. So, uh, any examples of sockets anyone can think of circuit programming?
One example, yeah, one example,
With
not in
sockets.
programming, more in networking side.
Mm-hmm.
Yeah. So
Yeah.
when we have a client and client is sending a request to server, so client app in OSI model, client application layer want to communicate to server application layer, and it in between these two applications layer, socket is a logical connection.
Mm-hmm. Mm-hmm. Yeah.
Or
Yes.
we can create
Yeah.
a chat application using socket where it create a channel between client and server.
Mhm. Yes. Any kind of APIs you can think of?
And in case of client server communication also at times from HTTP web application to have a bidirectional communication setup, then we implement WebSocket.
Yes.
Not sure this the same concept here also. I mean, what we are
Yeah.
discussing,
Yeah. 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 Sockets.
but that's
Sockets
one
are
example I know.
Yeah. Sockets are socket in networks and socket in distributed systems are same. We are just here looking at it from inter-process communication perspective and not exactly from network communication perspective. But it's the same concept.
Okay.
Yeah.
Multiplayer
So,
games can be one of the example wherein
yes.
multiple players are connected together and they kind of play together, right? So data has to they need to have a persistent connection, and data needs to
Mm-hmm.
be reflected across all the parties at the same time, almost at the same time. So sockets could be powerful mechanism which can be used for such use cases.
Yes. Yes. Yes, we can read. You all can read more about like are the circuits are really used for gaming applications or not. We can even I need to check that. So, but that's an interesting application. I agree.
I think all the web server communication from the client browser all happening on the sockets using these some ports. Similarly, like uh, in any FTP servers also like that. So these kind of application are using the sockets.
Yes. So yeah. So sockets is yes in all the applications that we discussed so far. Yes, I see that sockets could be useful. Now, whether the, sockets are used or any other mechanism is used, might depend on the challenges that they might have observed when using sockets, or what are the advantages of using sockets against other approaches. But yes, sockets are very powerful. They are uh, ideal for building customizable, scalable, and also robust communication systems. They are quite powerful. We'll learn more about sockets in the later slides as well. Other than that, the remote procedure calls. Anyone? RPCs? Anyone works with RPCs?
Ma'am, the from application sometimes we call database procedure. Is it the same RPC there also as an example?
Yes, it could be. It could be. Yes.
Okay.
Basically, these are procedure calls from one address space to another, where we call a procedure located in a different address space, which could be on the same machine, or it is on any other different machine across the network. So, uh, unlike the traditional functions, here in RPC, we need explicit cooperation between the client and the server process. Both sides have to agree on this procedure interface, and what will be the data that will be flowing, what will be the format, and what will be the communication protocol that will be utilized. So, in Unix specifically, RPC is implemented on top of sockets. Here, uh, what helps with using RPC is you get the flexibility to handle the underlying network communication, because you don't have to think more about like how the socket programming is happening underneath, or how the network programming is happening. The developer will only have to write code as if it's calling some local function. But when the system gets this function, it takes care of the serialization, the transmission of data, and also whatever response it has received, getting that response from the system, other system. And hence, anyone can think of any examples, or anyone has been using. So basically, RPCs are widely used when in client server architectures, where clients will make some request through a function, and the the server the will then respond to this request. So hence, RPCs are very important, or very foundational when it comes to distributed systems, and whatever currently the modern microservices that are happening, the RPCs are very critical. So now we've seen uh, what is IPC, what are different types of data structures that can be used for IPC, or approaches that can be used for IPC. Now, what is the role of IPC? Let us understand that, especially in the context of cloud computing. So, in most of the modern cloud-based architectures applications, these are typically split into microservices, as we all know, right? Which run across virtual machines or containers. Now, these services need a very reliable way to communicate. And that's where this interprocess communication, or IPC, comes in. IPC, basically it enables coordination between different components, distributed components. Now, this allows these different components to share data, synchronize, and also work with each other uh, efficiently, basically. And without this, we cannot build scalable and modular applications. So, uh, now, what are the different common mechanisms which are used in IPC, especially which are used in cloud? The first one is remote procedure calls, which we just saw. This allows one service to invoke another almost, another service almost like it is calling a local function. You feel like you are just calling a local function. If you use message queues, here these are ideal if you want to have some decoupled or asynchronous communication between different services, because you do not need a dedicated communication, but this can take care asynchronously. If you use shared memory or pipes, these are great, but they have to be on the same machine or on the same host. The You can use sockets or use HTTP, which is widely used. This can be between different services and different containers and the VMs that we have. You With all these different IPC mechanisms, they form the backbone of the communication that we have, or what we use when it comes to distributed cloud systems. So now we will learn each of them in detail. So before we start, maybe if you want, we can take a 5 minutes break and then we continue. If you want to just take a walk and come back, we can maybe continue after we start at around 9:20. Okay, so let's begin. Yes. I hope I'm audible. Okay.
Yes, ma'am.
So, yeah. Now, to understand how this process communication works, uh, we have to understand, especially using sockets, we have to understand how this communication happens over a network. That is, how each layer in the network plays the role. So, in the application layer, which is the top layer, we here is where what happens is the user protocols and services are available, and when we write distributed applications we interact with this layer the most. For example, http for web services, the grpc for if there are any remote procedure calls. Now these protocols handle things like the message formatting, the session management, and what are the service endpoints. When your application sends or receives a message, it has to go through this layer, but underneath there are other layers which also you know ensure have to do some kind of heavy lifting to ensure that there is communication happening. So in transport layer there are two major you know protocols which do the task, that is tcp and udp. Anyone wants to talk about these? What is the difference between the two? Which one we
Trans
should prefer? Why is yes, yes,
yeah, one is connection oriented, another one is connection less. So TCP, which is transmission control protocol, it would establish the session where it needs to source and destination and then would transfer the packets. UDP is not connection oriented, which is connectionless. So it sends the packets, does not wait for acknowledgement, and if it is, that's so generally TCP is more reliable. However, UDP is more quick, but it's not that reliable.
yes. You're correct. You've mentioned the two very important points. TCP guarantees the delivery, but it is heavier. It also maintains the order and takes care of the error correction. But UDP is still, preferred in some cases where you need faster and lightweight. But UDP will not deliver the guarantee. It will not have the guarantee of whether there will be delivery or what will be the order in which you will get receive the packets. So TCP is mostly used where there is gRPC or HTTP, but UDP is used for any examples anyone can think of.
DNS service or any broadcasting kind of they used UDPs.
Yes, yes. So where there is, let's say, video streaming, which is live video streaming, or as you mentioned, there could be DNS queries where the speed is very important. But if there is some loss of data, it's acceptable. On the network layer, this is the layer which ensures that the addressing and routing happens correctly. So this has to determine the best path that the packet has to take to travel from a source to destination for a network. And here is where the IP comes into picture, which handles things like what are the IP addresses which are assigned to the machines, and how do we route these packets from one machine to another machine based on these IP addresses. And what happens at the physical level layer? basically the Ethernet cables, Wi-Fi signals, switches, network cards, through which this is the layer which handles framing, error detection, and also translates these digital signals into electrical or optical signals, which are then transmitted physically. So one of the most common methods, as we discussed for IPC, is using sockets. Socket is an endpoint for sending or receiving the data across a network. You can use both TCP or UDP. You use TCP when you want reliable transmission. You can use UDP if you want faster, connectionless communication. Sockets are very important. They are the base for many high-level protocols such as HTTP or gRPC. So, how the socket programming works? The common system calls for socket programming from server side are the server side will have a function socket which will create a new socket. It will have a function which is bind, which will uh, ensure that you attach this bind function will attach a specific IP to the your port. So what happens here is you take the IP address that you need for your socket, you attach it to your here. Then there is a function which is listen, which will wait for incorporating what is the incoming connection. Once you receive the incoming connection, you accept it from the client. On the client side, what the socket does is client only has to create a socket and it has to connect to the server's IP port. Now, these four functions on server side and two on client side have now established the connection. Once the connection is established, then there are two functions. One is send and the other one is receive. So you can see that in this figure as well. The socket, the server will call a socket function, then bind, listen, and then socket will on the client side will just connect. Connect will then synchronize with accept. Once the synchronization happens, the next thing is to communicate. You write or you read. You write will go to server. Whatever you want to read from the server will be sent and sent from server to your client and so on. So this communication can then take place as long as we need it over time. And once both have finished the communication, then it's the time to close the communication. So if you if you want to try this in Python, it's quite easy. You can create a TCP socket in Python using these functions, and then on server side you'll need this, and client side you'll need a socket and connect. On server side, socket, blind, listen, and then if there is any acceptance. You can, if you're interested, you can spend some time and try this out using Python because most of you are comfortable Python. So now we have socket programming, but when we are having inter-process communication, a very critical thing is the security. Why do we need secure communication? There are some points here. Anyone wants to elaborate?
Just to avoid anyone who can intercept any communication, critical information like any critical data, logins, or any other information.
Yes.
So just to we need to secure the communication channel while we create a connection between client and server, and then just start transferring the data after that.
Agreed. So,
So,
what is a man in the middle attack?
example, if I am trying to get something on my server, and in
Mm-hmm.
between that one, man in a middle attack will treat as a requester and will try to put their uh, bugs inside your request body itself. When you
Mm-hmm.
send a request body either in TCP/IP protocol or any protocol, like here in a communication itself, so that will be in between your send and reach to server in between.
So,
Yes.
Ma'am, it will
Yeah.
be a interception between the connectivity from the sender and the receiver. One man will attack
Yeah.
particular package and uh, did not receive from the other end. That is known
So,
as.
so
Yeah.
I think it's what happens is it's kind of port mirroring. Whatever the communication is happening, if somebody is able to intercept, would be able to port.
Mm-hmm.
I mean, mirror that port, and entire communication will be copied. So he might be able to use it for malicious intent down the line if there is something, which is critical, because not the entire communication is all the time is critical, but if he is able to come across critical information, he would be able to use it down the line for that. So I think,
Yes.
just like somebody mentions, it could be the credentials which you would be, passing on throughout the communication. So man in the middle is basically able to intercept your communication. I don't think they would be able to, change that. It's just they can use that
Yeah.
information down the line.
They can alter. They can alter messages. It's possible.
Okay.
Yes.
ideally, any communication happening, and in between someone uh, pose as an, uh, I mean,
Mm-hmm.
as a valid sender, and then they just like someone said, like they route the traffic via their malicious host, and then they alter, they change the integrity of the data, and then they put on their all malicious content, and that is how that ideally it is actually kind of uh, altering the data and putting their own data in between the communication.
Yes. Yes. So yes, altering is possible. Even if you do not alter, using that data is also another issue that can happen. So that way, man in the middle attacks are can affect the data that is being transferred, and hence we need some a secured communication, something like a SSL or TLS, which will ensure that the data that is being transmitted is not tampered, and uh, you know we uh, so the example could be, let's say if you're trying to log in, if you're trying to do a payment or an API call. In such very critical cases, security is not optional. We cannot take risk with such cases. It has to be secured, and specifically in distributed systems. And if it is not secured, we will not be able to trust the system. And hence, this is the foundation of trust between all the components that we are using in a system. Hence, security is very critical. So, SSL is one such secure communication that we can achieve. SSL is now replaced by TLS. But so why do we communicate? Why do we need secure communication? As we say, whenever processes communicate, especially through network, there is always a risk that the data being transferred can be intercepted, altered, or even spoofed. And hence, whenever you are transmitting such sensitive information, specifically the passwords, personal data, financial transactions, we have to ensure that our communication is private. At the same time, it's trustworthy and has to be encrypted. Now that's where the SSL or its current successful, successor TLS comes into picture. So what is a SSL? Anyone?
SSL is a certificate in, I mean, whereas there is always a requester like client where the public and private keys, the certificate composed of public and private keys, and the keys are exchanged during the communication, and some public keys are shared, and then the private key is used by the client during the communication when they start doing the handshaking process, so that server can recognize and then allow the communication.
Yes. So
It's basically for
so it's a hmm, hmm,
encryption of your data. Like example we discussed in the early slide, like when we said credential and anything that should be encrypted over a communication channel, and for that this SSL plays a very important role to exchange a key, private key from a server, and then encrypt with the help of that key, so that even in middleman will take your data, that data will be encrypted data, and they will not get actual data because they don't have a private
yeah.
key which server shared to client, something like that.
Yes, yes, yes. So basically, SSL is a protocol which operates above the transport level layer. It is typically above your TCP, on top of your TCP, and this uh, ensures that there is secure communication between two machines. And the TLS, anyone knows the what is the full form of TLS?
Yeah, transport layer socket, I guess.
Security, yes, transport layer security. But still, many people call TLS as also SSL because SSL became so popular. So basically, it provides this very three important properties. One is confidentiality. Because of encryption, it can't be read by others. You get integrity, that is, it ensures that the data has not been tampered with during the transmission. And again, authentication. This confirms that the party you are communicating with is the one who say that they are the one that you want to communicate. This is done using anyone? How the authentication is done? Anyone knows?
Certificate.
Yes, digital certificates are used for the authentication. So, how does SSL work? Is through handshaking. So, before the communication begins, the SSL first does the handshake, that is between the client and server. The client will contact the server and it will say, I want to initiate the connection. Now, the server will then respond saying that this is the digital certificate that I have, which will have your public key. Now, the client will take the certificate, it will verify it against whatever trusted certificate authority it has there. If it is valid, the client will generate its secret key. It will encrypt it with the server's public key and it will send it to the server. From this point onwards, both sides will use this shared key to encrypt and decrypt the data. So, if it could be you're trying to send some user login credentials from a client to your server without SSL, anyone on the network can get these. But because your SSL data is encrypted using public key of your server and private key of your client, it gets encrypted. And even if someone intercepts it, it is not readable. So many in many socket libraries and even in the RPC frameworks, you can wrap your existing socket with SSL using just a few lines of codes. You can use Python as well, and this provides you a secure, connection for your socket. So these are two, three lines that you can use. Here we are using a built-in Python library for SSL, which uh, basically gives you access to the TLS. Here you first, create the context, which will create the SSL context object. This so this basically is used to get what is the version of SSL you want to use, which certificates are trusted, what are the verification policies and encryption algorithms that you want to use. So once you create this context, you can also use a default context as in this example. So, so you can create this context. Then once the context is created, then you have to, set up the secure default configuration, and then you use the wrapped up socket. Now this will help you that to take, the existing, if there is any socket that you already have, the socket gets wrapped up with the SSL or TLS functionality. So basically, you are telling the SSL context that this is the socket now, and you encrypt all the communications that are happening through this socket. So,
Ma'am, can you please
so
explain it again about the context types of it?
so in
What is the
context you have to
yeah.
so in context you have to mention what all you'll be, what all you'll need in this particular SSL. Like what should be the encryption policy, what should be the, you know, what should be the encryption, sorry, what should be the verification policy, encryption algorithms, you know, if you need anything specific, those can be mentioned here. Or if you can go for a default context, which will have some default functionalities. Okay. And then once you create this context, now you have already created a socket. So this socket, you when you do wrap up, so this context is set to that socket. So now socket will follow the rules which you have set for this context. Is it clear?
Okay, so for every socket, we must assign as this context actually. So a context is nothing, it's a
Yes.
kind of rules and
Yeah.
policies we generally
Yes, you
apply, right?
want for the for
Okay,
SSL. Yes.
okay, thank you.
So yeah, I was talking about now architecture in first previous few slides. So there are two types of architectures. One is master slave. The other one is the client server. So in master slave, you have one master node which is responsible for assigning the tasks to the slaves. It then monitors their progresses. It combines the results. The slave node is supposed to be like workhorses. They receive the task from the master. They have to execute those independently, and once they complete task, they have to send periodic updates to the master, or they might have to send the final result back to the master. Now, where do you think this kind of a system will be useful?
Any web application.
Yeah, in code like Jenkins, where we perform the master slave architecture.
So generally, master slave architecture we use especially in a kind of high availability environment as well, like clustering and all. So
Yeah,
uh, where
like a
work
map reduce.
correct, yeah.
Yeah. So, but what do you think could be a limitation?
Uh, so in terms of high availability, the 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 limitation is like the nodes which is acting as a master and the slave. So slaves will be like the utilization of those resources will not be optimal in that case. So
Depending
only
on, yeah, depending on the application.
depending on
But
the application.
fault tolerance, if it is not designed well, then if the master fails, the whole system will be unresponsive.
Yes, so that is where we have to define that within the slave like which will be acting as a secondary master, right? So,
Yes, yes. So yes, advantages is that there is simple control logic. There is only one node who is responsible for coordination. So it's easier to implement, manage, and control flows is also quite easy. The the advantage also is that the master has all the global view of what all the tasks are, what are the resources, how to allow for better task distribution, and how do we make debugging and logging easier for different slaves. But this is also a disadvantage. Single point of failure. If the master node goes down, the entire system can fault. If the system is less fault tolerant, unless you add mechanisms like backup masters or failover protocols, this could be an issue. Another issue could be scalability. As the number of slave nodes increase, the master might struggle. It may not be able to keep up with all the communication and coordination tasks that it has to do. This could create a bottleneck with the master, and this can be a issue when it comes to horizontally scaling more and more things. So while the this type of a system with a master slave model is simple and effective for small and moderately sized system, but if you need enhancements such as distributed coordination and load balancing for large scale or fault tolerant systems, this may not work. So what could work here is a client model. So this works specifically client server architecture specifically. If you use with along with the powerful option of RPC, that is protocol, remote procedure call. This is a very powerful abstraction when it comes to distributed system. Now, what happens in a client server system? The server will provide services and the client requests them, and the two may be different machines. They could be on different machines. They could be on the same machine. There could be a network or through messaging on the same or through shared memory. Now, when we have RPC specifically, what happens is RPC, lets the client call the procedure function, whichever it needs, and the client gets a feeling that it is doing this locally, but it is actually running on the remote server. Hence, when using RPC, distributed programming feels like any other normal function calls that we have, because RPC abstract this networking logic. We do not have to worry about this networking. For example, let's say if you want have a function like get user data, and you mention that this user is a number 42 user. Okay, what we cannot see is that behind the scenes, this call is serialized. This is sent to the server. Server executes it, and that the result is sent back to your network. But for you as a client, you can only see the function get user data. So how this happens or how this is done is basically there's a concept of stubs. Anyone knows what a stub is? So this is similar to sockets where it is a position. So there is a client stub and there is a server stub. Client stub is supposed to peg the arguments that are needed and send those the request to the server, and the server will then take this request that is received, it will unpack, execute, and return the result. So what happens here is you do serialization, that is what is called as marshalling. Now, anyone knows what a marshalling is? So, marshalling is the process of converting data or an object which is converted into a format that can be transmitted over a network. And this data or format is then unmarshaled, that is reconstructed by the client. This is known as marshalling. So now, so what do you think are the challenges and advantages, disadvantages of using RPC? Anyone?
I think in any way of RPC communication, it requires lots of communication processing. Uh, it is something will result in some way at the latency and the performance.
Yes, yes, good, good. It's latency or network failure handling is needed. I agree. Any advantage?
Client and server are hosted on different machines, so server can cater to a number of clients.
That is there. For anyone who is using RPC, for them it is very easy. It feels like writing a local function because you do not care about what is happening in the background. You RPC provides you the abstraction. You have to just write a function that you need in the background. The call to the server will happen. The data will be received, and you will receive the data back. So this helps you, this in having a better code modularity and writing reusable codes like reusable functions. But the challenges, as you mentioned, the are latency and network failure. Other challenge could be that what if there is a version mismatch between client and server, and error handling also sometimes can be trickier. Now, an example could be like, as you said, any microservice call which happens over gRPC, which is Google RPC. So, um, now, any can anyone tell me which architecture do you think is better, master slave architecture or client
Ma'am, I do
server?
have one question here. Um,
Yeah.
this can we say that master slave architecture with RPC, the client server architecture?
You can. Uh,
RPC is a kind of central library repository where
yes,
they
yes.
provide all the connections and all those things. We don't need to put create those connections, maintain those connections, and means it's kind of client server architecture is just master slave architecture with enhanced functions like RPC functions.
Mm, you can say that this client server is a type of enhanced master slave architecture, but uh, here there could be multiple clients, multiple servers. So there is no one master as such here in this case.
Okay, so
Uh,
client can also work as a server means
yes,
it's a kind
yes,
of distributed. We can say like just
yeah.
take an example of a distributed system like Bitbucket, where every
Hmm.
client has their full repositories and they can do their changes and once a while they communicate with the server and push the changes. So every client
Yes,
work as a server.
yeah, yeah, yes. A good example. So now let us see how a RPC or remote procedure call works in this client server architecture kind of a scenario. As I mentioned, client does not directly call the server's function. It will call a stub. Now the client stub will act like a local representative of the this remote procedure, and this stub will take the function parameters and then it will marshal them. That is, it will put them together in a format, and then it will then send this marshal data to for transmission. Now, once the server receives this data, marshal data, it will unmarshal. It basically decrypt kind of marshalling could sounds like encrypting or decrypting kind of a system. It unmarshals and then the server will use this data, the byte stream it has received, reconstruct the original parameters that were sent, and then the actual server function is executed with these arguments that you've received from the client. Once you complete the task, the results are then marshaled and then returned back to the client. They're sent to the client stub, and then once the client receives it, he will again unmarshal those, and then those results are presented to the local function, whichever has called the client function. Is it clear how this works? Any doubts here? This, yeah, this is pretty straightforward. So, yeah, now what is gRPC? Anyone has used or worked with gRPC? Okay, so as I had mentioned in the previous slide, gRPC is Google Remote Procedure Call. It's an open source RPC framework which is developed by Google and is available for the users. This helps us to uh, this allows clients and servers to communicate transparently, and it's easier to they build these connected systems. So how gRPC works is it has we can define this gRPC using a dot proto file, which is a protocol buffer, then generate the client and server code from it, and then the server will implement the service and the client will call the service remotely. Now, for a secure RPC, the way you use SSL in sockets, you also can use SSL with your RPC. So many RPC frameworks, uh, you know, have to uh, have to use the functionality of SSL or TLS, specifically gRPC or you know HTTP. This here, what happens is the data is encrypted and then transmitted between the client and server. So even if someone intercepts, they can't read them. Also, you can set up mutual authentication using the certificates. So both server and client verify each other's identity, and this then helps to have a trusted and secure channel. And we are able to take care of any critical or sensitive operations like financial transactions or even transferring the credentials as we discussed earlier. So now let us come to how do nodes discover each other in this inter-process communication. So in distributed systems, it is very important that nodes know who else is the part of the system. How do we know? So this is what is called as node discovery and membership management. So simplest method is obviously using IP list, but this is very hard to maintain. And i- if what if the IP changes? So then it will fail. A slightly better approach is using DNS based discovery. Here, services can find each other using the host names. But in many modern systems, we also prefer dynamic membership protocols. So there are these three types of protocols. The first one is gossip based protocol. Here, rumor spreading happens basically, where each node shares what it knows with random others. Okay. There is another approach, which is heartbeat. So in heartbeat, what happens is nodes regularly ping each other. Are you there? Are you there? And if there is failure to respond, then they disconnect. So that's how heartbeat with timeout works. There are some special tools such as Zookeeper or etcd, which are which act like a centralized service, and they help and maintain consistent memberships. So, and people who are membered or who are coordinating with this centralized services, they are quite they are considered, they are active and are used in most of the cloud native architectures. So now, how do we check if the node that is there in your uh, distributed system which is trying to communicate is active? So health monitoring is very critical in distributed systems, and this ensures that all nodes are functioning correctly. When we say a node is healthy, we generally mean it is responsive by ensuring that it is using acceptable level of resources like CPU and memory, and its application logic is also running as expected. We are getting the results that we need to monitor if a node is active and healthy. There are different methods. The first one, simple. A simple ping can check if the node is reachable or not, right? Heartbeats again are periodic, signals which are sent by nodes to indicate that they are alive. I'm there. I'm there. I'm there. If a heartbeat is a missed, then okay, the node has failed. Mm, There are some more sophisticated systems than a ping or heartbeat, such as agent-based monitoring. One example is Prometheus node exporter. What it does is it will collect CPU, memory, and disk metrics for real-time insights of all the nodes that exist. You can check this system, and then this can help tell you that your node is healthy. So, how do we take care of fault tolerance? What if a node crashes? So, fault tolerance is very important because it ensures that the system continues to operate even if some parts of it are failing. So, we typically what we do is we use fault tolerance, like we check if there are crashes, network splits, or master node has failed, and to detect how if there are any faults, we use timeouts, which tells us if there are any unresponsive nodes. There is a concept of retry, which helps deal with any temporary issue. Let's say if there is a packet loss, we resend it and check if it is delivered. If there is anything serious that has happened, you can use consensus algorithms like Raft or Paxos, These are used in distributed systems where a consistent state is checked if for some nodes, even if the some nodes fade, we are we are still in a consistent state that is checked using this algorithm. So if the master node fades, what you can do? One, you can have conduct the election as soon as the master fails, or conduct it before it fails as a backup option. So leader election protocol, you can have a backup master which is always available on standby, or the keeper that we discussed can coordinate and decide who is the next master if one master node fails. So anyone has worked with MapReduce and wants to tell us about MapReduce, how it works? So MapReduce is a very classic example of how a master-slave, architecture works. In MapReduce, a single master manages coordination, and it assigns tasks and keeps track of tasks and statuses. In case if a worker node fails, that is, if there is a crash or disconnect, the master simply reassigns the task to any other worker. This ensures that there is fault tolerance. Also, we can, all the tasks that have happened can be tracked persistently, and we can allow if the recovery, if there are any failures, and we can also prevent any kind of duplicate execution that is happening in this system. So, what all we have discussed today?
No, sorry. This MapReduce example you said it. Can
Yeah.
Kubernetes also be an example? Master worker, because Kubernetes also have this infrastructure where there is a master node handling all those communication coordination, all the and I mean directing all those stuff and all to the worker nodes and all. And in case one master is failed, then another will be uh, uh, started like that. So can we consider this one as Kubernetes also in this
Yes,
case?
yes, Kubernetes is also master slave architecture. It is called control plane and worker node architecture. Yeah,
Yes.
because control plane is the master, right? In that.
Yes. Yes. Yes.
Yeah, and worker nodes are the slaves. But it is master node. Yes, master slave
One more
architecture.
example here is Databricks. When we are using a managed Databricks where we have a data plane and the control plane. Like control plane is again here master, and data plane is where your actual notebooks and all the Python's library, whatever you are trying to build on your Databricks is running. That is on data plane, and control plane is like a master node. And in a previous slide, you shown some etcd. So I think in Kubernetes, that is the one who is managing the consistency of other nodes, node discovery, that etcd.
Okay. Yes. So yeah, etcd. Yes, etcd is anyways how it's a way to store the distributed key values, right? And it
Yes.
so it is used in multiple systems.
Ma'am, Kafka we consider as a master worker architecture because in the Kafka, so Kafka brokers handle the operations and the zookeeper which do the elections between the nodes. So can it be the example of master worker architecture or master slave architecture?
So yes, the examples that we have just discussed, the um, Kubernetes is master slave. The MapReduce is also works like master slave, and even the uh, yeah and other example other than these two you want. I need to check the Databricks. I am not very familiar with. I'll have to check it. But these two do follow the MapReduce and the Kubernetes.
Ma'am, this map reduce is algorithm. What is this? It's technique.
Hmm. Yes, it's a technique. It's basically an algorithm. Yes.
Ma'am, could you please
Very
explain
popular
once?
in distributed systems. Hmm?
Could you please explain once MapReduce task?
Yes. So what happens here? It's basically MapReduce is you can call a programming model. This programming model MapReduce is used basically to process large data in you do it in parallel across a cluster of computers. So you here have a mapper which will take input data, it will process it, and it will create some key value pairs, and then the reducer that you can see in this figure, it will take the output from this mapper, it will then aggregate the data, and it will produce the final output. Okay, so how it works is the input data is split into smaller chunks, and they are then given to different systems who process them in parallel. And this then the mapper will process the data, and then it will create whatever are the important pairs. These pairs are given to the reducer. It will then reduce these pairs of data and produce whatever is the final output. So whatever conclusion that needs to be taken, that will be then created by the reducer. Is it clear?
Yes, ma'am. Thanks.
So, yeah. So basically, MapReduce is a very powerful programming model which helps you to process large amounts of data in parallel. It first splits the data, gives it to mapper. Mapper finds the key. Then it provides those keys to reducer. Then reducer then finally, then concludes or finds the final reduces it and gives us the data that we need to process. So it is used mostly, it's very popular for big data processing and any data analytics kind of systems. So we'll take this example even in the in future and discuss more in detail on MapReduce. So you if even if there are any doubts now, this will get clarified.
Ma'am, one more question here.
Yeah.
As we discussed this Kubernetes clusters, I can relate the map with the scheduler of the Kubernetes, but I'm not able to relate the reducer. What is the reducer functionality in the Kubernetes cluster? Scheduler will
It's
schedule the task, partition the task, and schedule to the multiple resources for the processing. And then how are they going to consolidate? Means reducer. What is the function in the Kubernetes?
See, Kubernetes is for container orchestration, right?
Yes,
Orchestration, and it is basically for deploying and managing containerized applications. But
yes.
MapReduce is not meant for data analytics. It is supposed to reduce data because we
Okay.
cannot go through the huge
Yeah,
amount
got
of
it. Got
data
it. I
and make
think
any
that this
sense
we
of it.
can't relate. We can't relate. This is for the big
Yeah,
data
there is no
analysis.
direct connection. There is no
Yes,
direct,
sir.
yeah, direct because both have different functionalities. It's not the same. Both are doing.
Okay,
The
got it.
application for MapReduce is completely different than Kubernetes.
Yeah.
Okay? Yes. So, um, yeah. So, in summary, we have learned about interprocess communication. We have seen the different techniques that we have, sockets, We have seen how we can introduce securities with SSL. We can use both with sockets as well as RPC. We have seen the architecture of master and slave, and we know that if we want a reliable system, it needs discovery, monitoring, fault tolerance. So here are some Q&As. I want you all to spend time on it, think about it, and we will start our next session by discussing these questions. And then in the next class, we will learn about MPI and how we can try doing the first lab of your course. Okay. Any other doubts?
Ma'am, do we need to think programming in terms of program or directly like how we can implement heartbeat and all those kind of things? As a system design, we have to think, or in terms of program, we have to think.
No, as a system design, I want you all to think about, not for
Okay,
programming.
thanks.
Yeah. So yes, I have clarified this before. We will need C programming. It is we cannot learn or play with all the parallel and distributed, program models without knowing C. So you will need C. You you will have to learn at least the basics, and you know there are tools which are available now, so it shouldn't be difficult. But we cannot oh, start with Python or use Python. Sorry. Because most of these parallel and distributed programming models need low level, optimizations, and those cannot be achieved using Python. Yes, PPT is enough. I agree. I also spoke to the build team that the handout topics do not directly connect with the textbooks, and hence that time they suggested that ensure that I have enough material in the PPTs, and I have also put references. I'm sorry, I think I didn't show the references. I put references, so I'm putting references whichever I'm going through using, and I'll keep doing that so that if you want to read more, you can visit these.
Thank you.
Yeah. Yes. Okay. Thank you. Let's meet in the next class. Yeah.
Yeah, thank you, ma'am.
Yes. Thank you.
Thank you.
Yeah. Thank you.